Hello, my name is Kelly Caldwell and I'm the lead instructor at Stanley Community College's Instructor Training Center. This is going to be a lecture on one of the many modules in the different courses inside of Cisco Networking Academy. I'm going to cover many different items in these particular lectures, starting with CCNA, going possibly all the way through DevNet. But to begin with, one of the things I want you to know is I go with a good enough philosophy, and that is no lecture is perfect. So in other words, if you're in the classroom with me, we could be interrupted by a person knocking on the door, my phone could ding, your phone could ding. I'm not going to have perfect lectures, and therefore my recorded lectures will not be perfect. You may hear my phone ding, you may hear a phone call start during one of the lectures, and I'll pause the lecture and then start back over. I'm trying to give you a good enough lecture to help you learn the materials. I also want you to know if you are not taking classes at a Cisco Academy, in other words, you're watching these videos on my YouTube channel and you're not trying to participate in an actual Cisco Academy, I strongly recommend that you go to www.netacad.com, scroll all the way to the bottom to where it says Find an Academy. I'm going to put in here the city that we are in. So in case I am in Albemarle, NC, North Carolina, as you can probably tell by my accent. But you'll see here Stanley Community College, and if you click here, you would get the information on what courses we offer and how to get in contact with us and how to actually see our offerings. So if you are in an area and you would like to find your local school or Cisco Networking Academy, then go to netacad.com, scroll to the bottom, and do Find an Academy. I strongly recommend that you get involved in the Cisco Networking Academy because it is a wonderful, wonderful program. Last but not least, enjoy, learn, and grow. So enjoy these lectures, learn from them, grow. If you want to grow in the IT field, that's excellent. Or if you just want to learn new things, that's even better too. We hope these lectures will be useful for you and that you will be able to use them to increase your knowledge in the IT field. Hello and welcome to a lecture on Module 4 of Introduction to Networks version 7.02. We're going to talk about the physical layer today. And the physical layer, if you remember from our Module 3 presentation, you will remember that the OSI model, which is a reference model, and we call it a reference model, if you remember, because a reference model does not actually map to any real-world protocol stacks. Although I do know some of you will say, well, there was an OSI protocol stack, which yes, there was, but it wasn't used and is not in widespread use. But the OSI reference model had 7 layers: the application layer, the session layer, the application presentation, session layer, transport, network, data link, which is broken down into the sublayers of LLC and MAC, and physical. So layer 7, 6, 5, 4, 3, 2, 1. So layer 1 is the physical layer. And remember, we said for this particular item, if you wanted to remember it with a mnemonic, all people seem to need data processing, layer 7 to layer 1. Or please do not throw sausage pizza away, which is layer 1 to layer 7. And we talked about how layer 1 is our bit pusher, our blue collar worker, or we get down into here, our media and mediums, and how we make ones and zeros on our particular media or medium. We're going to talk here a little bit about the purpose of the physical layer, some of our physical layer entities such as copper cabling, unshielded twisted pair cabling, fiber optic cabling, and wireless, and what they do for us in our networking. So we're down at the lowest layer now, and we're going to talk about how important this is. You'd be amazed the number of times in the real world I go to troubleshoot a problem and find that a cable has been plugged in the wrong port, and that is a physical layer problem, or the wrong type of cable has been used, or the cable is bad, or a transceiver, which is a layer 1 device, may be bad. So be aware, the physical layer is very, very important on our networks. So what does it do? It provides connectivity to our networks. So it could be a cable using Ethernet, like this particular router here has a 4-port Ethernet switch, and then a 1-port Ethernet that goes to your incoming DSL or cable modem connection. It could be wireless connection. Now here's a wired connection where we've connected this cable, by the way, would be a straight through patch cable from the PC to the device. It could be a wireless connection. Okay, now right now we're showing wired again. This, by the way, when you start talking about wired connections and a physical layer component, cables are physical layer components, as are these RJ45 transceivers. They're considered a physical component. And in fact, the network interface card here that's built into the NIC or into the PC itself, you could say that this connector that this transceiver plugs into is also a layer 1 transceiver, but it's built into the NIC, and we will learn that network interface cards are predominantly layer 2 devices. So data link layer devices. So here we are at the very lowest layer, and that is the layer where, again, we're encapsulating. I think this is now the 4th time we've seen this video, but we're encapsulating the data with a TCP header. Then we're going to put an IP header on it, and then we'll put our frame header or Ethernet header on it. And then finally, we'll convert it to ones and zeros. The physical layer is this cable right here, and the processes needed to convert your data into a series of ones and zeros on that cable. If it's copper, it's going to be electrical pulses. If it's fiber optic, it'll be light pulses. If it's wireless, it'll be some type of wave or RF wave. So our physical layer standards are typically set by the ISO, TIA, EIA, ANSI, IEEE. All of these are those organizing bodies or standards organizations that can set our physical layer standards. But the beauty is, as we talked about, this physical layer in our most common actual real world reference, or excuse me, protocol model, TCP IP, which is a true protocol model. We remember there's 4 layers. We've got the application layer, which does the job of the application, presentation, and session layers of the OSI model. We have the transport layer, which does the exact same job as the transport layer in the OSI model. We have the internet layer, which maps to the network layer. And then we have our network access layer. And this maps to the data link and the physical layers. And if you remember from our last lecture, I mentioned that when TCP/IP was created, they did not specify any required data link or physical layer components for TCP/IP, which means it can run across any of these particular types of cable and any type of medium that we need for our communication to occur. So the physical layer is made up of physical components, cables, transceivers. You will learn that there's a thing called a repeater, which is a layer 1 hub, or a hub that can do repeating. There's encoding, how we encode those ones and zeros, and then signaling standards. So let's look, we've talked a little bit about the physical components. We'll talk more about those as we move forward, but let's look at encoding. So if you're running a older Ethernet standard like 10 base T or 100 base TX, it may use Manchester 4.5B encoding or Manchester encoding. This is basically the presence or excuse me, the transition of a particular voltage will result in a change in the number. So in other words, we see here, we've got, it's presence or absence of voltage. So if you've got a voltage, then you've got a 1. If you got no voltage, you've got a 0. You'll notice here, it's during this middle time of each time period that we have, we're actually looking at whether or not we have a voltage or no voltage. You can also do it depending upon changes in voltage. So in other words, this could be obviously a change in voltage or a presence or absence or a particular voltage and another voltage. You can also do it with just transition states. So if it stays the same voltage, it would stay a 1. If it changes, it becomes a 0. So here you're looking at the presence of voltage on these two, means those are both 1s. The presence of no voltage or a different voltage at a time slice means it's a 0. So that's Manchester. 0s by high to low voltage transition, and the 1 bits as a low to high voltage transmission. So it can be either no or a low to high or high to low. Once that transition occurs, you look in the middle of your time slot, and that's where timing becomes such an important issue. If there isn't, if you don't have a way to measure time slots, you have no way of knowing that it has transitioned from a higher to a lower voltage or from a lower to a higher voltage. and you measure it in the middle of the time slot. But this is what's going across each individual copper wire as communications are taking place between two devices. There are other schemes that are much better for high-speed Ethernet, but Manchester was one of the earlier ones. Here, voltage over time, which is one of the ones we use for anything that's using a copper cable. So that could be unshielded twisted pair, shielded twisted pair. It could be other forms of copper cabling. Fiber optic cable uses light pulses, so the presence or absence of light pulse in a time frame. Now it's important. Notice everything is based upon a time slot. So it's a voltage in time or a transition of voltage in time that will determine whether or not there's a 1 and 0. That becomes important when we talk about concepts such as crosstalk or interference from other electrical sources, because if other electrical sources can cause the voltage on a particular cable to change or to be altered, it can actually corrupt the data going across a particular piece of cable. Fiber optic, really you can't change or corrupt the data with any outside source, so it's pretty much more, well, it is more resistant to crosstalk. It's completely resistant, in fact, to crosstalk. But it is a series of light pulses based upon a time unit. So if a pulse is there, you see light, that could be a 1. If there's no light, it could be a 0. Wireless media, again, we're looking at different frequencies over a time frame. And so we can look at AM, FM, or pulse modulation. And so these can be used to determine when there's a 1 or a 0 on the individual line. Now here you can see voltage with digital signals. If there's no voltage, then it's a 0. If there's voltage, there's a 1. So, or if you were using Manchester encoding, it would be there's a low voltage situation, it transitions to a high voltage, then you get a 1. If it transitions back to low voltage, you get a 0. If it goes to a high voltage and stays high voltage with Manchester encoding, it will consider that in those 2 time slots, those will be 1s. And so that's how we can make our 1s and 0s. By the way, computers are not very smart. They can count to 2 and that's it, 1s and 0s. So it's very common for people to think computers can do anything, and they can, but you have to do it all through the use of binary encoding. Now, I want to talk to you a bit about bandwidth versus throughput and goodput. Now, I want you to consider and think about a garden hose, okay? You've got a garden hose, and you hook that garden hose into a spigot. When you connect it to that spigot, your bandwidth is the complete amount of water that could run through that hose if you turn it wide open and fill the hose completely up. So your bandwidth is the most that you could transfer through a particular medium at any time. All right. It's based upon the properties of the physical media. So for instance, again, the example I give you, if a garden hose can only carry a small amount of water compared to a fire hose, which is much bigger. It has more bandwidth. All right. When we're looking at bandwidths, we measure them in bits per second, which is the fundamental unit of bandwidth, or kilobits per second, which is 1,000 bits per second, or megabits per second, which is a million, or gigabits or terabits per second. The big thing though is remember, bandwidth is the most that can be carried across a physical media at one time. Throughput, and again, let's go back to our analogy of a garden hose. You hook your garden hose up, but you only turn the water on partially. So you, at that point, your throughput, the amount of water coming through the garden hose, is not equal to your bandwidth because you're not completely filling up your garden hose. So throughput is the amount of data or bits going across your network media at that instant in time. Sometimes throughput could be made to match bandwidth, because if I turn the garden hose wide open, as high as it'll go, then the throughput going through that garden hose will be equivalent to the bandwidth. The other thing we have to worry about, and we'll come back to latency, but the other thing we have to worry about is what's called goodput. And that is because just because you have bandwidth of 100 megabits per second doesn't mean you're always going to be able to put 100 megabits worth of data through that particular pipe. The reason being, imagine, again, going back to our garden hose, let's imagine that for heaven forbid, a spider or a dirt dauber, we have dirt daubers in North Carolina, which is a type of bee, has gotten up in your garden hose and created a small nest. Well, at this point now, your garden hose has something that's reducing the amount of throughput that is available on my garden hose. Likewise, in our networking world, we have things such as retransmissions, we have control data, we have three-way handshakes, we have protocols that require certain items to take place on the network that do not actually move data, but still take up bandwidth. So goodput is the amount of traffic minus any overhead, any of that overhead needed to establish protocol connections, encapsulations, or to retransmit. So typically throughput, goodput will not equal throughput, and goodput and throughput will typically not fully equal bandwidth. So even though you have 100 megabit per second connection, you may only get 80 megabits down and 10 or so megabits up, and that's probably a 10 megabit up there. The last item we need to think about is delay and latency. Anytime you add any device on your network, be it a layer 1 device or a layer 2, which is a switch, or a layer 3 routers or multi-layer switches, you are introducing latency. And that is the delay it takes to get from one side of your network to another. We're going to learn that for unshielded twisted pair, the maximum cable run is 100 meters or roughly 328 feet. Now, the reason that is important is because you're going to learn about standards where devices have to look on the cable and see if anything else is using the cable. Well, they're using the concept of latency and the fact that we know it takes a certain amount of time to get from one side of the network to the other. So we're going to limit that to ensure that our protocols will work effectively and that we don't have to worry about late collisions or other issues that can occur when we exceed the specifications for our physical layer components. So again, I want to do a quick review. Bandwidth is the maximum amount that can travel over a media or medium. So the maximum amount that can go through your garden hose. So if you get a 4-inch hose, you got more bandwidth than a 1-inch hose. Throughput is the amount of information moving through that particular media at a time, in a slice in time. So again, if you've got a 1-inch garden hose, but you've only turned it halfway on, you've got a 1/2 inch of water going through your garden hose. Goodput is the amount of data being moved on our networks minus any overhead traffic. So even though you've got throughput, let's imagine I've got, let's say I've got 100 megabits per second connection. All right. My throughput at this moment is 55 megabits per second. That may still only mean though that my goodput may only be 40 megabits per second, depending on the network, because I may have 15 megabits of overhead traffic. And that's just, you're normally not going to have that much, but you could. It's possible. So be aware that goodput is the data actually being moved. All right. So let's look at some copper cabling. Characteristics of copper cabling: it's cheap, it's easy to work with. It is not resistant to EMI very well at all. Now we do have shielded twisted pair cabling, which is a little more resistant to EMI. But electromagnetic interference, I always tell people in my classes, what are some of the best creators of EMI? Electric motors, generators, nuclear weapons. Of course, I always tell them if a nuclear weapon goes off, we really don't care about whether or not our networks are working. But EMI can cause havoc with copper cabling. So can crosstalk. So if you lay a normal unshielded twisted pair cabling across a high powered electrical cable, you can end up with interference. And if that happens, you can end up with something like this. You end up with, this is what you wanted, but due to this crosstalk that is taking place, so this is an outside electrical signal here on number 3, you end up with 4, and it actually changes the meaning of what is inside of there. Now, this would be caught more than likely at the CRC level of the frame check sequence at layer 2, but then you're going to have to retransmit. So anytime crosstalk is an issue and you have to start doing retransmits, your goodput goes down. But be aware of that. That is it. Types of cabling, unshielded twisted pair, and you'll notice if I zoom in here a little bit, it's a little hard to see on this, but this white, blue, blue, white, orange, orange, white, green, green, white, brown, brown, you can actually notice they have a different rate of twist for each one of these pairs of wires. And that is to attempt to make it to where the crosstalk will not be in sync with one another. So the signals, the electrical signals going across these wires will not actually cause crosstalk among these wire pairs. In shielded twisted pair, and there's multiple ways of doing this, you can have each individual pair wrapped and then wrapped also in a shield, or you can have the pairs wrapped in a shield. Shielded twisted pair provides a little more protection against EMI and crosstalk, but still it's not absolute by any stretch of the imagination. And then we have coaxial cable, RJ6, RJ58, 59. RJ6 is what we use now mainly for our inside of our houses for TV, satellite. My home, when I built it, I actually put in over 3,500 feet of unshielded twisted pair and over 1,500 feet of coaxial cable. If you ever build a house, when they got the walls open, that's the time to run your cable. Because regardless of what people say, wireless is great, but wired is always faster and it's more secure. So here we have unshielded twisted pair. We can look at our cable here. It's got a jacket. I will tell you one thing about the jacket to be aware of is there's a thing called plenum rated cabling. And plenum, technically, depending on the fire code in your area, anytime you run cabling above the ceiling or under the ground or in the walls, you may have to have plenum rated cabling, which is cabling that when it burns, the sheath will not put off a noxious gas. All right. Here's shielded twisted pair. In this example, you can see how they've actually wrapped the individual pairs in a shield and then wrap those pairs again in an additional copper shield. It's just a little harder to work with because you have to pull these back when you're creating the cables. And in coaxial, we have our cladding, we have our center core, which can be stranded or it can be solid, depending on what kind of cable you buy. And then we have our BNC connector here, N type and F type. BNC is either known as a bayonet connector or British naval connector, depending on where you read. So that is our copper cabling. Now we have an entire section here on UTP, and in fact, the beauty of UTP cabling is that you can have it inside of your classroom and you can teach your students how to make cables. We can actually go in and easily create cables. Now this, back in the, well, there's still multiple standards now, but category 3 was basically rated for up to 1 megabit per second. Actually 10, I believe you could actually do 10 on category 3. Category 5 and 5E was 100 to 1,000 megabits per second. Cat 6 up to 10 gigabits per second. Cat 7 was also a 10 gigabit standard. And now Cat 8 supports up to 40 gigabits. We use a lot of Cat 6 in our data center to connect devices that have 10 gigabit Ethernet connections. But we also use a lot of SFPs now instead of, which are copper SFPs, to support 10 gig connections because they're just a little bit easier to work with. Here we have the types of plugs used on Cat 5. That's a bad picture because it should not be that squat. It is an RJ45 connector, which is an 8-pin connector. It looks like a big phone plug. Here's our UTP sockets that can be used on patch panels. And then this is an example of a very poorly terminated unshielded twisted pair cable versus a properly shielded cable. Now, we actually have the ability, and you need to learn and teach your students the difference between a straight through and a crossover cable. There are two different standards, 568A and 568B. The only way to really know these standards is just to learn them. But you will see the only difference is that A and B switch the places of the white, green, green, and the white, orange, orange. So with 568B, it's white, orange, orange, white, green, blue, white, blue, green, white, brown, brown. You'll notice on both of these, there's no striped beside each other and no two solids beside each other. So there's no stripe, stripe, or solid, solid. Same over here. If you make one side 568B and the other side 568B, you've got a straight through. Or if you make both sides 568A and the other side 568A. If you make one side 568A and the other 568B, you've got a crossover cable. We needed to use these back in the day before what's called auto cross or MDIX, MDIX. And we had to have crossover cables. In today's world, most things will cross over for you. So even though you may be connecting two like devices, so a PC to a PC, you can use a straight through cable and they will auto cross themselves. Likewise, if you connect technically two switches to one another, you're supposed to use a crossover cable. However, with auto cross, it will do it for you automatically. And then a rollover is what our console cable. If you remember our console cables, and literally a rollover cable, and I'm going to turn my camera on for just a second because I can actually hopefully find a connector here. Pull out a cable. A rollover cable is important because, well, they're only used by Cisco, but if you ever get in a situation where you don't have one and you need one, you can make one. And to make a rollover, you would just make one side 568A or B, and you would take the cable or the device. Or I should have had this out before I started this example, but that's one of the reasons why I say these are not perfect lectures. It's something I do to make it useful. So this is a 568. Let me actually turn off my background, virtual background, so it won't be causing a problem. Okay. So here is a 568, or actually an RJ45 connector. If typically when we create cables, we line our cables up. This is white, green, green, white, brown, white, orange, blue, white, blue. This is actually a 568A cable right here. But what I would do to make a rollover is I would make one cable, and on one side, I would put the end on with the tab away from me, okay? And that's typically how we make our cables. We put the tab away, so pin 1 is on this side right here. Let me pull it up. Let me pull this over to make sure I'm on my video is showing. So like this, if I had my pin away, this would be pin 1 right there. And so I'd put one side to make a rollover, put it on with the tab away. On the opposite side, I would put the tab towards me. And what that does is it literally rolls all 8 pins over. So pin 1 on one side maps to pin 8 on the other side. And that is literally a rollover cable. I'm going to turn the video off now. All right. So this is an example of 568A. So go up here and you can actually drag out white, green. Well, it'll let me do it. I've actually had some issues with some of these drag and drops, especially with a touch screen, and this is on a touch screen, so that's why I'm not able to do it. You'll be able to do it though, and here it is. It's 568A, white, green, green, white, orange, blue, orange, white, brown, brown. I actually literally just remember 568B, white, orange, orange, white, green, blue, green, white, brown, brown, and then remember that all I have to do is switch my oranges and greens, and I've got 568B. Okay. Now, having said we can make all these cables, in the real world, we buy our patch cables unless we just get desperate because a machine can make them so much faster and better than a human. The other we have, folks, is a very special type of cable called fiber optic cabling. Now, fiber optic cabling can be single mode fiber, which is a single core and is developed to have a single laser firing through it. And it is actually designed for lasers to go through it and for long haul applications or long distances. And then multi-mode, so down here we can see we got a glass core of about 9 microns, 125 micron diameter glass cladding, and then you got a polymetric coating. And typically outside of this, or even in this, you've got some type of carbon fiber or some type of protection to protect your cable, because if you pull it too hard or if you take it in too far of a bend radius, you can actually break the glass inside. Again, single mode is a single path for light. Multi-mode is designed, and it's still a glass core. It used to be years ago they would actually use a plastic core. No more. It's all glass cores of 50 to 62.5 microns. A glass cladding of, again, 125 microns, and then coating. And then this allows for multiple paths of light that can bounce around inside the multi-mode. Typically, multi-mode uses LED emitters versus lasers, whereas single mode uses actual lasers. Either way, never, ever, ever, ever look into any type of fiber optic cable, even if someone on the other end has absolutely promised you it's not connected, because it can instantly destroy your retina. Do not. Only use testers when you're working with fiber optic cable. Don't even put it on your hand to try to see if the light will show in your hand, because technically it should not be able to burn you, but some of these lasers are very, very powerful. Where do we use fiber optic? Well, anywhere that we need to be totally secure, because guess what? You can't tap fiber optic easily. Am I saying you can never tap it? No, it's been done, I'm sure, but it's harder to tap. Number two, it's completely resistant to EMI. Number three, it is one of our cabling methods that has the biggest bandwidth. In fact, we really don't know what it can carry maximum, because we haven't been able to develop the technology to make it to where we can't use it. So it's got huge bandwidth capacity. We're also using it now in runs in our networks anytime there's large needs for 40, 100, even higher gigabit connections. And when we do that, we've got a couple types of connectors that we use. Now, these STs, if you ever have used them, I call them simple twist. That's how I remember. STs, you have to push them on and twist them. So simple twist connectors, even though they're called straight tip connectors, I call them simple twist. SC they click in. So I call these, even there's subscriber connectors, I call them simple clicks, because they click when they go in. The other thing you can remember too, folks, is fiber optics are always going to come in a pair. You got a send and a receive. So make sure, depending on how your systems are set up, that you plug the send on one side to the receive on the other, and vice versa. We have these lucent connectors simplex. Okay, so singles that click, and then we have duplex mode LC connectors that actually mold the send and receive pair together, and you click them in. And that way they're already made to be send to receive on each side, so they're rollover basically, or excuse me, crossover. Now they're starting to work it now where you can do both, so you can actually send and receive on both a single connector, but you'll still typically see these in pairs. So here's some patch cables. This is again, simple click is what I call it, although it is a subscriber connector. You'll see simple click patch cord, LC patch cord, and then you can get them in all types of variations. You can get a twist to a click, and so on and so forth. It just depends on what you need. So why is everything not running on fiber? Well, first off, fiber optic cabling is more expensive. Okay, it is a little harder. Well, it is harder to install because you have to have specialized equipment and skills, and you got to have more safety precautions, because again, even when you're putting ends on fiber optic cabling, if you get a piece of fiber optic cabling in your skin or in your eye, you're in very big trouble. However, saying that, if you have any instance where you need complete immunity to EMI and RFI, or you need immunity to electrical hazards, and a great example is where I'm sitting right now. Our campus sits on a large hill. It is a lightning magnet. If we were to run copper cabling between our buildings, we would be building a large antenna that would definitely get struck by lightning. That's why we run fiber optic cable between our buildings, so that we don't have to worry about it getting struck by lightning. Okay. Plus, we can run at greater speeds and longer distances with that fiber optic cabling. All right. Our last media is wireless media, and wireless is great. I always tell people though, if you can wire it, because if it's wired, it's more secure and it's faster. It will always be faster. Well, not always. Okay, take that back. Not always. The only reason I say that is because at my house, the internet that I can get in is DSL, and it's 10 megabits per second, whereas my phone can get LTE connections, and so I'm actually got a faster wireless connection than wired. However, typically, even in my house, everything I can connect wired, I connect wired. Wireless media, you do have to think about your coverage area. Again, the building I'm sitting in is actually two buildings that were built at different times. And so the front part that my office is in was added to another building. And so we had to actually, in this building, put in double the amount of access points for wireless, because there's actually an exterior wall right behind where I'm sitting here that used to be the outside of another building. So we ended up putting a building to a building, and you've got a really, really good block there for your wireless. It is a shared medium, and I think that's one of the biggest things people don't realize is that wireless LANs do operate in half duplex, which means only one device can send or receive at a time. So we'll learn about access methods, and the different one that is used by wireless LANs, 802 wireless standards, use a different access method that we'll talk about as we move on to the data link layer in module 6. However, having said that, it is good to be able to use wireless, especially with your phone, with your laptops, to be able to move around, to go outside, sit in the sun. We'll have much more on wireless as we move forward in your CCNA studies. And that is pretty much all there is to the physical layer. And actually, the physical layer is one of the most important components, because I tell students all the time, and I make a little bit of a joke, but I talk about if you don't have blinky lights, nothing works. In other words, you think about it, power is a physical layer component. And I have actually had troubleshooting issues before when the device simply was not powered on. And so the physical layer is a very important component. And in this particular module, you learned about what the physical layer is. You learned about copper, fiber, and wireless media. You also learned about the concept of throughput, bandwidth, goodput, and latency. We mentioned also a little bit about crosstalk and attenuation. I did not really define attenuation, so let me do that while I'm here. Attenuation is a concept that is important with the physical layer, and attenuation is the loss of signal strength as a signal moves over a medium, moves through a medium. A media or medium. So think about it. Anytime you're going across cable, if you're an electrical signal, you've got resistance. So attenuation is that loss of signal strength. That, by the way, is how we get this 100-meter distance run limitation for UTP. Past that, you would have too much attenuation for the signal to be able to be received in the proper form. So I hope this lecture on the physical layer has been useful, and you'll come back for our lecture soon on the number system.